Modern 3D graphics systems allow users to create and animate increasingly sophisticated worlds. Despite their inherent three-dimensionality, these systems are still largely controlled by 2D WIMP user interfaces. We are interested in exploring the enormous potential of 3D interactive techniques to provide solutions to modeling and animation problems. In this video, we present an expressive 3D animation environment that enables users to rapidly and visually prototype animated worlds with a fully 3D user interface based on 3D devices and virtual tools. In our environment, there is no intrinsic difference between user interface and application objects. The application is represented as a single network of objects connected by multi-way constraints. Constraints are maintained using a lazy evaluation version of SkyBlue, a domain-independent local propagation algorithm that can satisfy a hierarchy of multi-way, multi-output data flow constraints. During interaction, the user is the source of an information flow that propagates from input device sensors to manipulated objects. User interface components act as mediators using their internal constraint networks to transform users' motion into objects' modifications. The constraint bidirectionality makes it possible to interact with dynamic environments, opening the door to the integration of interaction and animation techniques. By recording the effects of users' manipulations on application objects, all the expressive power of the user interface can be exploited to define animations. To obtain compact, editable representations of continuous parameter evolutions, we have developed a data reduction algorithm that incrementally builds from a sample parameter evolution a B-spline, preserving value and timing of each sample within a given tolerance. Novel interactive solutions to animation problems are made possible by the tight integration of all elements of our system provided by the constraint-based architecture. In particular, animation tracks can be synchronized by interacting during playback. Since playback constraints are weaker than interaction constraints, the user can take control over animated objects. The orientation of the constraint network connecting a parameter to its track tells the system when to override previously recorded data. In the remainder of this video, we illustrate our approach with interactive sequences showing the visual construction of complex 3D animated worlds composed of thousands of constraints. All demonstrations were recorded live and were not edited. The user interacts with the synthetic environment using 3D device configurations and interaction metaphors. Shutter glasses provide binocular perception of the synthetic world. A spaceball is used for continuous specification of spatial transformations, and a mouse is used as a picking device. Keyboard commands trigger mode changes and animation playback. Since our main research goal is to explore the possibilities of 3D interaction, we do not provide any two-dimensional graphical user interface. The virtual camera is controlled by the spaceball using the eye-in-hand metaphor. A mode change makes the spaceball control a 3D cursor using the node-in-hand metaphor. The 3D cursor, represented here by a hand, allows the user to interact with the synthetic world. The user can grab a model by pressing on a mouse button. While grabbed, the model is constrained to follow the motion of the cursor. Motion parallax, stereo rendering, and interactive shadow casting provide the necessary depth cues for 3D perception. Collision detection helps the user to precisely position models with respect to one another. The amount of information defining a 3D models and the ways that could be used to control it are enormous. Directly manipulating the models is only a partial solution, since it implies that the user knows what to manipulate and how. Our system guides the user's manipulation through visible mediator objects. We call these objects virtual tools. Virtual tools are first-class objects that lie in the same space as application objects, and that can be manipulated using the same techniques. Their visual appearance is determined by a modeling hierarchy, while their behavior is controlled by an internal constraint network. The desire to manipulate a model with a tool is expressed by binding the tool to the model. The binding action consists of selecting an active part of the tool, called binder, and identified by an icon, and then dragging a line from the tool to the model. At the moment of binding, the tool decides whether to accept the connection by checking the type of the model. When bound, the tool changes its visual appearance to a shape that provides information about its behavior and offers semantic feedback during manipulation. When a tool is bound, the user can manipulate the connected model by selecting parts of the tool and by moving or pressing them with the 3D cursor. Information propagates through the constraint network from the tool to the model. The direct correspondence between manipulation and effect on the model makes it simple to understand the tool's behavior. Unbinding the tool expressed by dragging a line to empty space removes the constraints that connect the tool to the model, changes the tool's visual appearance back to the unbound version, and moves it back to a default place called the shelf here on top of the table. Multiple tools can be active simultaneously in the same 3D environment in order to control all its aspects. At the top of the image we see a light tool, a composite tool that displays and controls the information contained in a light source. The light tool is composed of a cone subtool which controls the light projection, a body which controls its position and orientation, and two binders, the objects in front of the light, that makes it possible to constrain the light's position and orientation. For example, by connecting the arrow-shaped binder to a model, we force the light source to always point towards the selected model. While this connection is active, the light's look-at behavior is always realized. The bidirectionality of the constraint allows the maintenance of the look-at relation during manipulation of the tool, or the manipulation of the connected model. Multi-way constraints are essential to provide such a tight coupling between application and user interface objects. Through virtual tools, we gain interactive controls of both geometrical and non-geometrical attributes. For example, we can manipulate the color of the light with the material tool, containing a three-dimensional slider that controls a color in the RGB cube. Various tools may be used simultaneously to control the same information, providing multiple views and multiple interaction metaphors. Here, a second tool is used to change the intensity of the light. Thanks to bidirectional constraints, the states of the light and that of both the tools are consistently maintained during manipulation. Virtual tools provide a means to interactively add behavior to components of the synthetic environment and are not limited to simple editing tasks. For example, by connecting a tool encapsulating a walking engine to a skeleton model, we provide the model with a walking behavior. When the tool is moved, it makes the skeleton follow the 3D cursor with a walking cycle animation. Disconnecting the tool from the model removes this behavior. Now, when the skeleton is moved, no walking cycle animation occurs. Our fully 3D user interface provides the expressive power required for continuous control of all aspects of the synthetic world. The same techniques used for manipulation may therefore be used to define animations. By recording the effects of users' manipulations, we can create hand-sketched animations, much as curves can be hand-drawn in most drafting tools. In particular, sketching the animation path allows the direct specification of subtle synchronizations between position and orientation components. The amount of information collected by recording the interactive session is much too large to allow effective editing. A more compact representation must be obtained. The data reduction technique must not only preserve the geometry, as in drafting tools, but also the timing of the initial data. We have developed an algorithm that incrementally builds from the input sequence a parametric B-spline, which preserves the value and timing of each input sample within a given tolerance. This spline, defined by a small number of points, can be interactively edited with the same tools that we use for splines created by keyframing. Here, for example, the character's path has been reduced from the initial 90 samples to 8 control points for position and 6 for rotation. This performance-based approach complements standard keyframing systems by providing the ability to create animations with straight-ahead actions. It provides complete control over the path's geometry and timing, while keyframing offers control only at a limited number of points. Recording the effects of the user's manipulations allows us to exploit the full range of interaction techniques and behaviors provided by our 3D user interface. In this way, we can define the animation of all kinds of attributes. In particular, constrained or free motion can be easily specified, as here for the definition of the light's motion. The new path is scheduled by default at the beginning of the animation. Now, to have the light continuously pointing towards the character, we interactively add a look-at constraint to the light by connecting the tool's orientation binder to the character's head. During playback, the added behaviors participate in the animation and may override previously recorded motion. The light's orientation is now determined by the look-at constraint, while its position is determined by the recorded path. Synchronization among the different components of an animation is an important issue. In our system, animation is represented as a time interval hierarchy, and the temporal coherence between the hierarchy levels is permanently maintained. By interactively connecting start and end time binders, animation tracks can be synchronized. Here, for example, by connecting together the start binders and the end binders of the characters and light tracks, we constrain both motions to be performed in parallel. The animation of the light's orientation is modified by the look-at constraint in response to timing changes. Another way to synchronize animations is to manipulate the environment during animation playback. Here we define the animation of the light's intensity with the mediation of a tool which allows remote control of the light's parameters. The resulting splines are automatically synchronized with the rest of the animation. During playback, information propagates in the constraint network from the animation tracks through the light and down to the tool, which is forced to display the light's state changes. We can easily specify animations involving complex synchronizations by using constraint manipulation during playback. Here, we use constraint manipulation to define a camera panning motion by sketching only the camera's position. The position of the camera is controlled by the user, while its orientation is determined by the look-at constraint. This is easily modeled using hierarchical constraints by setting the priority of interaction constraints higher than that of playback constraints. During playback, the view from the camera is rendered in real time at the bottom right of the screen. We have presented an integrated environment for the rapid and visual prototyping of 3D animated worlds. The constraint-based architecture provides enough flexibility and efficiency to model complex animated 3D environments. Pose-to-pose as well as straight-ahead animations can be specified with a fully 3D user interface. Data reduction provides the ability to edit animations created by interactive performances. In our future work, we intend to develop new virtual tools and visualizations that will improve our 3D user interface for discrete and continuous track manipulation. To allow the system to adhere to timing requirements, we are developing time-critical techniques for controlling rendering complexity and constraint evaluation.